All right, today we're diving into something that sounds like it's straight out of science fiction. We're talking about a programming language, but not one that runs on a computer chip. This is a language designed to control physical reality itself. Let's get into it.
So, picture this. You've got a surgical robot in the middle of a delicate operation, or a massive factory arm moving tons of steel around. What if you could write a program for that robot that was absolutely mathematically guaranteed to finish its job? No bugs, no crashes, no getting stuck in some infinite loop. That very question, that's the key to this whole story.
And this is the answer. Gerald 2026. Now, this is not your typical language like Python or Java. It's not built for crunching numbers or running apps. Gerald is built to describe physical movement, things like rotations and translations. You can almost think of it as an assembly language for motion itself.
To really get what Gerald is all about, we actually have to start with what it can't do. Because you see, when you're dealing with high-stakes robotics, sometimes the most important features are the ones that are intentionally left out.
You know, in computer science, being Turing-complete is usually the gold standard. It means your language is so powerful it can solve any computable problem, given enough time and memory. But Gerald? It's designed on purpose to not be Turing-complete. It's limited, and that intentional limitation is precisely what makes it so incredibly safe and predictable.
This table really just lays it all out. A universal computer, a Turing machine, needs things like infinite memory and complex control structures like loops. Gerald has none of that. It's just a simple, sequential list of instructions. It reads from top to bottom, does the thing, and then stops, every single time. In that last row, that's the whole ball game. Gerald programs are always terminating.
And that right there is the magic trick. If you don't have infinite loops, a robot arm will never get stuck spinning forever. If you don't have crashes, its behavior is always predictable. For any machine that has to interact with the real world, that kind of guarantee isn't just nice to have, it's everything.
So how does it actually pull this off? Well, let's look at a famously weird, but Turing-complete language called brainfuck. All of its power comes from these two little bracket symbols. They're what create loops. The safe version of Gerald's genius is that it just doesn't have them. You take away the brackets, you take away the ability to get stuck forever. Simple as that. But, well, the story isn't over yet.
Because what happens if you decide to add those little symbols back in? The source material puts it perfectly with this one German phrase. This changes everything.
Okay, so let's move into the next part of this story. Let's talk about a theoretical version of Gerald. What happens when we take this perfectly safe, predictable language and we just add a tiny bit of that dangerous complexity back into the mix? Just these three symbols, a left bracket, a tilde, and a right bracket. That's it. They look so harmless, don't they? But these three characters completely shatter all the safety guarantees we just talked about. And in doing so, they unlock a whole new universe of possibilities. Here's how it works. The brackets, just like in brainfuck, bring back control flow, the ability to loop and repeat actions. And that little tilde symbol? That introduces memory. It's like a command that tells the robot, hey, remember this exact position and orientation you're in right now. And once you have a way to loop and a way to remember things, well, you've got all the pieces you need for a universal computer.
And the implication here is just profound. With these changes, Gerald is no longer just a safe way to tell a robot what to do. It becomes a language that can run any algorithm you can possibly imagine. But the computation isn't happening on a chip. The robot's physical movement is the computation.
So what does that even look like? I mean, really? What does it mean for an algorithm to become a physical movement? Take a look at this code. This isn't running on some server in the cloud. This is a sequence of physical movements for a robot arm that literally calculates the Fibonacci sequence. The arm moves, it stores its own positions in space, and then it physically adds those movements together to find the next number in the series. It's wild, right? Abstract mathematics becomes this concrete physical process. The robot arm isn't just following a list of commands anymore. Its actual motion is the calculation.
Or how about this one? This tiny, elegant little piece of recursive code tells a 3D printer how to build a complex fractal. It's not getting thousands of lines of G-code with coordinates. It's using a simple physical loop to create that infinite-looking complexity. And that leads us to the final, and frankly the most startling part of this whole thing. What are the consequences when that line between software and physical reality just dissolves? In computer science, there's this famous unsolvable problem called the halting problem. It basically asks if it's possible to know if any given program will ever finish or just run forever. With this new Turing-complete Gekal, that abstract theoretical problem becomes terrifyingly real. Look at this program, R-Lamin dot. All it says is rotate and then loop. The result? A machine spinning in a circle forever.
Think about that. This isn't a blue screen of death on your laptop. A software bug is no longer just an error message. It's a never-ending physical action. And that could be useless at best or catastrophically dangerous at worst.
This just opens up a whole new paradigm. I mean, you could write physical viruses that just lock entire factories into useless, endless loops. But you could also have swarms of drones performing complex computations just by flying in formation. A sorting algorithm is no longer just code, it's a robot physically putting boxes in order. Physics itself becomes programmable.
The source material calls this brain fuck for the real world, and that's just the perfect analogy. But instead of changing bits of data in a computer's memory, you're changing physical states in the actual space-time continuum.
Which of course leaves us with this one final massive question. In a world where an algorithm and the physical execution of that algorithm are the exact same thing, what does that do to our understanding of information, reality, and risk?
The ultimate conclusion is as simple as it is staggering. Physik wird zur Software. Physics becomes software. Thanks for watching.